Welcome to The Explainer. Today we're diving into a seriously elegant engineering triumph over at Pinterest. We're going to look at how they tackled this massive hidden infrastructure problem that was just quietly eating up resources and money. It's a completely fascinating story about machine learning, network architecture, and why, honestly, sometimes the absolute best code you can write is the data you simply choose not to send.
So think about this for a second. What actually happens when your servers are literally too fast for your network? It's kind of a maddening scenario, right? You've got these incredibly powerful, cutting-edge machine learning models ready to make lightning-fast recommendations, but they're just sitting around twiddling their thumbs. Why? Because the pipe feeding them data is completely clogged. And this was the exact core conflict Pinterest engineering found themselves facing. They had all this massive compute power, but a critical network bottleneck was basically throttling their entire system.
To really wrap your head around this, imagine you're paying top dollar for a massive fleet of ultra-fast, heavy-duty delivery trucks. Those are your incredibly expensive AWS GPU instances. But instead of loading them up with valuable cargo, you're filling them to the brim with empty cardboard boxes, driving them all the way across the country, and then literally just throwing those boxes in the recycling bin as soon as they arrive. That is essentially what was happening here. The compute power was vast, but the network bandwidth was just completely saturated, moving discarded machine learning features around.
Okay, let's jump right into our roadmap for today. We'll be covering the root leaf bottleneck, the compression band-aid, send what you use, syncing the source of truth, safeguarding the system, and finally, the efficiency payoff.
Let's start with the root of the problem, pun absolutely intended. Section 1, the root leaf bottleneck, separating CPU and GPU.
So Pinterest uses what's known as a root leaf architecture. It's basically a separation of concerns. The root handles all the CPU work. It fetches the necessary ML features from the feature store and pre-processes them. Then it fans out those requests down to the leaf. And the leaf is where the actual heavy lifting happens, the model inference, typically running on these really high-powered GPU machines. Now, on paper, this is a beautiful, highly optimized separation of workloads. But in reality, it created a massive traffic jam right on the road between the two.
Now, to be fair, this setup definitely has some undeniable advantages. It simplifies model onboarding, mostly because you just add new leaf partitions. It drastically reduces queries to the feature store because all the leaf partitions get to share a large in-memory cache over in the root, and it optimizes resource utilization by keeping CPU and GPU tasks separate. But, and this is a huge but, here is the fatal flaw. The root serves multiple models, so to minimize requests, it fetches a massive union of all features any model might possibly need and then sends that entire giant payload to the leaf. The leaf models only use what they actually need and literally just discard the rest. Basically, they were sending everything to everyone, and the network simply couldn't handle it.
Which brings us to Section 2, the compression band-aid, shrinking unused data.
So, your network is choking. What's the intuitive, quick fix for a bandwidth problem? You shrink the data. Because these ML features had a ton of similarity and sparsity, meaning lots of zeros and empty values, they were actually highly compressible. So the engineers quickly enabled LZ4 compression. And hey, it worked. Somewhat. It dropped network usage by 20%, but it came at a pretty steep cost. It bumped up P90 latency by 5 milliseconds and pushed CPU usage up by 5%. Going back to our truck analogy, compression is just like squishing all those empty cardboard boxes down so you can cram a few more onto the truck. Sure, it's 20% better, but fundamentally, you're still wasting precious resources shipping empty boxes. It was a band-aid, not a real cure.
Okay, so we need a real fix. Section 3, send what you use. Trimming the payload.
The breakthrough philosophy here was brilliantly simple: send what you use. It actually heavily mirrors the C++ programming principle of include what you use. So instead of sending that massive union of all features down to every single leaf, the root would trim the payload. It would only send the exact features that a specific model actually required. They finally decided to just stop loading the empty boxes onto the truck in the first place.
But wait, how does the root actually know what the leaf needs? Well, the secret sauce lies in the model signature, which is exported as a file called moduleinfo.json. This file strictly defines the exact inputs and outputs of a given model. Think of this as your ultimate guaranteed packing list. By reading the signature, the system ensures it perfectly packs only the required features and absolutely guarantees it never accidentally leaves a critical piece of data behind.
But that introduces a new problem. Section 4, syncing the source of truth, safely updating configs. Models are refreshing constantly, so how do you keep everything perfectly synced without breaking things? Well, they didn't reinvent the wheel. Instead, they cleverly packaged those module_info.json signatures right into their existing deployment pipelines. They follow a super strict staged delivery flow. First, it goes to a canary testing environment, then through an automated canary analysis, and finally out to production. By doing this, the packing list rides the exact same operational rails and safety checks as the machine learning models themselves. It's a really elegant sync.
And since a root server doesn't just handle a single model, it serves entire bundles of them, the deployment pipeline generates a single, aggregated bundle-level artifact. What I really love about this setup is the built-in resilience. During the build, if a model version is somehow missing its signature file, the system just logs a warning and skips it. It doesn't fail the entire build and bring deployments to a screeching halt. It's a super pragmatic, robust way to handle errors.
Now, what's absolutely crucial is preventing a crash. Section 5. Safeguarding the system. Preventing data floods.
First up, they had to decide how to filter the data, and they wisely went with an allow list. That means tracking exactly what you do want to keep. The alternative would be a block list, tracking all the features you don't want. But given how ridiculously fast ML models evolve, a block list of deprecated or experimental features would just grow out of control almost instantly. Tracking only what you explicitly need is vastly more efficient, computationally way lighter, and honestly just so much safer.
And you've got to appreciate these fallback mechanisms. If the trimmer fails to initialize, it alerts an on-call engineer, for sure, but it deliberately does not block the host from launching, which preserves system capacity. If a request comes in for a missing model version, it just safely defaults to the latest version's allow list. And this is the best part. If a single model bundle gets corrupted on disk, the trimmer completely isolates the failure. It just keeps using the old safe version held in memory for that specific bundle, while successfully updating everything else. Literally, one bad file cannot trigger a cascading system failure. So, the golden question, was all this effort actually worth it? Let's check out Section 6, the efficiency payoff, real-world impact.
Get this. This single optimization allowed Pinterest to downsize their ads route cluster fleet by a staggering 27%. Just pause and think about the sheer amount of hardware that percentage represents. Because they weren't artificially bottlenecked by the network anymore, they were able to drastically shrink their entire physical footprint. And the drop in bandwidth brilliantly illustrates exactly how they pulled it off. Before they implemented the feature trimmer, the ads route cluster was peaking at 4 gigabytes per second of network bandwidth. After they flipped the switch, it absolutely plummeted to under 1.5 gigabytes per second. They literally cleared a massive traffic jam overnight.
And this absolutely wasn't just a fluke for the ads platform. That whole sand what you use philosophy scaled beautifully. They expanded it out to the home feed and related pins. Outbound route usage was essentially cut in half. Inbound network usage on the Leaf clusters saw an unbelievable 65 to 75% reduction. And all of that success allowed them to reduce the home feed route fleet size by a full 33%.
Which really brings us to the bottom line. Before, because of that terrible network bottleneck, they were basically forced to use really expensive network-optimized AWS instances, the M6 Ion series. But by dropping the bandwidth requirements so drastically, they were able to just swap those out for standard M6i instances. That one simple hardware downgrade, completely enabled by writing smarter software, resulted in infrastructure that is 20% cheaper across the board. They saved a massive amount of money.
It really makes you step back for a minute. We spend so much energy chasing more compute, faster processors, and bigger, wider pipelines. But as Pinterest brilliantly demonstrated here, sometimes the absolute purest form of efficiency isn't speeding up the work. In an era completely obsessed with faster processing, is the ultimate optimization simply choosing to do less? It's a pretty powerful thought to leave you with. Thanks so much for joining me on this explainer, and I'll catch you on the next deep dive.